Okay, suppose Aroldis Chapman, who is no longer with the Reds, but when I wrote this question, he was with the Reds. He can throw a 500 or 105 mile per hour baseball. We first have to convert that into meters per second, but let's see if he throws it straight up, how long the ball would be in the air, how high the baseball traveled, and what the baseball's velocity is when it reaches the starting location. So we first have to convert 105 miles per hour into meters per second. From the quiz, am I remembering 0.447? Yes, 0.447 meters per second per 1 mile per hour. Grab a calculator, figure out what that number is. Quite fast. I'll call it 46.9 meters per second. Draw a picture of what's going on. The baseball is going to go straight up, and then it's going to come straight back. Its initial velocity, I'll put it on the other side, initial velocity is at 46.9 meters per second. What's its final velocity up here?
0.
Now, and I'm only talking in a vertical direction. So 0 meters per second. What does the acceleration do to gravity?
9.8.
I will say negative 9.8 meters per second, thinking up is positive, down is negative. So if we want to calculate how long the ball was in the air, we first need to know how long it's going to take to get to its high point. What kinematic equation do we have using initial velocity, final velocity, acceleration, and time?
The last half of the distance.
Let's find an equation in our book. Should be late chapter 2 or early chapter 3. Something with an initial velocity, final velocity, acceleration, and time.
So it's the distance formula.
Distance is not one of our variables. Initial velocity, final velocity, acceleration, and time.
Oh, the A equals the change in velocity divided by the time.
So A equals change in velocity
I had that written in my
over time. Yes, because it comes from section 2, 3.2. VF equals VI plus AT, or V equals V plus AT, or VF minus VI equals AT, or A equals VF minus VI over T. A bunch of different ways you could look at this. So if we wanted to solve this for T, I'd multiply both sides by time over acceleration to get that the time will be the final velocity minus the initial velocity divided by the acceleration. So our final velocity was 0 meters per second. The initial velocity was 46.9 meters per second. Acceleration is negative 9.8 meters per second. That is actually going to be negative 46.9 meters per second divided by negative 9.8 meters per second squared. The negatives will end up canceling to give us a positive time. I will round to 2 decimal places, 4.79 seconds. Meters per second divided by meters per second squared will give us a unit of seconds, which is the variable for time. So it'll take 4.79, that's a very sloppy 4.79, 4.79 seconds to make it to the high point. The question I have is, how long is the baseball in the air? Once it's up high and it has a vertical velocity of 0, it becomes a free fall, and we would work this exact same problem backwards. We would just be swapping VF and VI and changing acceleration from negative to positive, and find that it would take another, or an additional, 4.79 seconds to return to its starting location. So the total time, actually over here it was the 4.79 seconds to the high point plus 4.79 seconds for the free fall. For a total flight time of 9.58 seconds. So when we have an object being thrown up and then it comes back down, to find the total time, we figure out how long it takes to get to the high point, and we double that. So it's just over 9.5 seconds of total time. Now we can go ask the question, how high up the baseball traveled? What is this distance here going to be? We can't do that until we know how long it takes to get there. So I'm going to go to a new page and write out what we know. We had the initial velocity of 46.9 meters per second. We have a final velocity vertically of 0 meters per second when it gets to that high point. We now know the time to that high point is 4.79 seconds. We know acceleration due to gravity is negative 9.8 meters per second squared. To know how high up the ball traveled, that's now distance, and we can then use the distance formula that was the VIT plus 1/2 a t squared. This distance formula actually doesn't use the velocity. Sorry, it doesn't use the final velocity, only the initial velocity. So we can plug everything in that we have. Initial velocity 46.9 meters per second. Multiply by 4.79 seconds, add half the acceleration of negative 9.8 meters per second squared times 4.79 seconds squared. I'm going to cancel units, then plug numbers into the calculator. Meters per second times seconds. Seconds will cancel, giving us meters. The acceleration has a unit of meters per second squared. Time squared has a unit of seconds squared. So this seconds, which gets squared, cancel that second squared, and we will have meters again. So we will be able to have meters plus meters. So our final answer will have meters in it. We can plug all of this into the calculator. 46.9 meters times 4.79, the seconds already canceled, plus 1/2 or 0.5 times negative 9.8, now I've changed the sign, times 4.79 squared. The time gets squared, and the distance it travels up is 112.2 meters. That's well over 300 feet. So the picture, this height is 112.2 meters if we ignore wind resistance, because in reality there is wind resistance. He can't actually throw 112 meters up. It is less than that, but this is in a frictionless physics land. So that is the height of the baseball. The last thing we want to know, what would the baseball's velocity be down here? If the initial velocity here was 46.9 meters per second, the velocity at the top would be 0 meters per second. We'd take 4.79 seconds to get up, 4.79 seconds to get back. What would be the final velocity down here?
Can you still use the change in velocity formula?
Don't even need that.
Isn't that what you just did back there where you doubled it?
It has to be the same.
Oh, it's the same. Okay.
Because it's the same time to go up, same time to go down. If basically the In the up situation, the initial velocity was 46.9 meters per second. The final velocity was 0 meters per second. So for the free fall, the initial would be 0. And if it's the same time, same acceleration, same direction of that acceleration, the final velocity going down would have to be the initial velocity going up.
Are you going to paste that together and look back at that?
Sure.
Please, would you?
Now, the next situation I'm not going to do yet because it's a little bit further along.
But that's still